Hello and welcome. This video tutorial serves to help with the homework gravitational force and field problems. In this homework, we'll be looking at 6 different problems. Universal gravity force with one-step problem, universal gravity force given the volume and density, and you have to find the mass, gravitational force on what's called a Kuiper belt object based on size and density, gravitational force on a satellite orbiting at some altitude above a planet, gravitational field strength. You'll be calculating the gravitational field strength at some altitude above a solar system body. And then finally, force gravity on a planet. Let's begin. The first question we're going to look at is called universal force gravity problem. The first thing I want you to do is go to the problem, put in your name so we can begin. So in this problem, you can see you're given the separation distance down here. Okay, now you can see in my example, my separation distance from the center of one mass to the center of the other mass is about pretty close to about 30, 32. I mean, I would say 32 and a half, but maybe just a little bit more than that. So I'm going to be listing certain things. So first I'm going to list that, and then I'll list the other things that are available in the problem too, such as what it's made of, its radius, its density, and its mass. Okay, so record the masses and distance to their center. So I'm going to draw a line from the center of one mass to the center of the other mass. And according to my picture, that line is about 32 point, uh, 32.6, maybe. You have to estimate. Okay. Record the masses of your planets. You can see what they are at the bottom of the table. First one for me is 3.69. So 3.69 times 10 to the 6th kilograms. Okay, this is a brand new unit for us. The unit for mass is the kilogram. Look at my other one. 2 times 10 to the 7. Okay, now looking at these, it's pretty clear that this has got to be my, let's see, let me fix this. Yeah, this right here has to be my object too, because you should look at it 10 to the negative 6, and then this is 10 to the 7. So that's fine. I just got them backwards. Um, so now what I'm going to do is I'm going to calculate the force of gravity between these. So to do that, we're going to use what we set up in our lab, and that is Newton's universal law of gravitation. We write it as F equals big G times M1 times M2 divided by r squared, where r is the separation distance between the center of the two objects. And remember, the value of big G is the gravity constant, and that number is 6.67 times 10 to the negative 11. Okay, so let's begin. Let's put all our stuff in. We're going to go 6.67 times 10 to the negative 11. We're going to multiply, and notice when we put this in calculator, we're going to go open parentheses, 6.67 times 10 to the negative 11 times your first mass minus 2 times 10 to the 7 times your second mass minus 3.69 times 10 to the 6. Then you're going to close parentheses. Then you're going to hit your divide button. Then you're going to open another set of parentheses. This is for the separation distance between the two masses. Mine would be 32.6, close parentheses, and then hit your x squared button. When you do that, you're going to get a value for force. Well, let's go ahead and move that. Looks like I'm getting a value of about 4.63 newtons. Newtons, N stands for newtons, is the unit of any force. So we have two brand new units, kilograms and newtons. Okay, so I've got my value for force. Um, and I'll put that in my program in a second. It says, is the force of gravity you calculated the force felt by the object on the right, or is it felt by the object on the left? It is felt by both. And what I mean by that is both experience equal and opposite force. So mass one is going to pull to the left, and then mass two is going to pull to the right, like that. Point 6 and what did I say? 4.63. All right, there we go. So hopefully you were able to get question one right yourself. If so, let's move on to question two. Now in question two, they're going to see some similarities, right? We're going to be given the composition of each object, its radius, its density. We're going to have to figure out its volume and its mass. Okay, so now keep in mind, we're assuming that these objects are somewhat spherical. So to define the volume of that, we're going to use the equation 4/3 pi r cubed, okay, to find the volume of these planets. Okay, let's put your name in the program and let's begin. Okay, so rock and wood are my two compositions. Go ahead and write in yours. 5.006. 4.192. Go ahead and write in your radii. Okay, density 1200 and 750. Okay, now from this, we're going to have to figure out the volume by calculating the volume of each sphere, and then we'll figure out the mass of each one too. Okay, let's just do that over to the side. So volume one would be 4/3 pi r1 cubed, and then volume two would be 4/3 pi r2 cubed. So you're just plugging in for radius, that's all. So the radius of one would be 5.06. The radius of two is 4.192. Okay, pause the video now and see if you can calculate each volume. Okay, well, my first volume turns out to be 525.48. So I'm just going to say zero point 0.5 cubic meters. Okay, and my volume 2, 4.192. So you have to make sure you cube the radius times pi times 4 and then divide by 3. That's how you'll put that in your calculator. Okay, for the second one, I'm getting about 308.6. Okay, so 525.5, 308.6. All right, so we got that. Now we need to find our mass. Well, density, if you look at the units, density is kilograms per cubic meter. Well, density, the variable for density is the Greek letter rho. Okay, that's the variable for density. And rho is equal to, as you can see, mass divided by volume. So if I want to figure out mass, you can see I just need to multiply both sides by volume. And that's how I'm going to figure it out. So mass is equal to density times volume. So let's figure this out. So mass 1 would be density 1 times volume 1. And then mass 2 would be density 2 times volume 2. Right, so that's what we're going to plug into. Okay, so now density 1 be 1200 times volume 1 is 525.5. Okay, mass 2, that's going to be density 2. That's going to be 750 times volume 2, which is 308.6. So go ahead and multiply those, figure those out. I'll figure mine out. Okay, you should expect your masses to be pretty big. Now you can write them in scientific notation or in normal standard notation. I'm going to write mine in scientific notation. I get 630,600. That would be 6.306 times 10 to the 6 kilograms. And then I got 2.315 times 10 to the fifth. Oh, I got to change that. That's 10 to the fifth power, not 10 to the sixth power. Okay, there we go. Okay, so I've got my two masses. Okay, 6.306 times 10 to the fifth, and then 2.315 times 10 to the fifth. Okay, now that I've got my two masses and I got my separation distance, there's my separation distance. Okay, and all I have to do is just scroll down a little bit. You can see my separation distance is about 27.2, maybe. Okay, estimate yours. Okay, my bigger mass, 6.306 times 10 to the fifth power. And then down here, 2.315, 2.315 times 10 to the fifth power. Okay, so I've got my two masses and my separation distance. Now that we have that, we can do our easy calculation for universal gravitation. Remember, we're going to start with open parentheses. Then we'll put in 6.67 times 10 to the negative 11 times the first mass, 6.306 times 10 to the fifth power, times the second mass. In my case, it's 2.315 times 10 to the fifth power, Okay, then close your parentheses, then hit divide. Okay, and then we're gonna put in the separation distance, which in my case is 27.2. Close parentheses, and then don't forget to square. Most people forget to square, and that becomes a pretty common mistake. So go ahead and pause the video, figure out your gravitational force. I will figure out mine. Okay, I'm getting a force of about point oh, whoopsie, 0.01316 newtons, something like that. All right, there you go. Hopefully you were able to get question number 2 correct as well. Okay, if you did, let's move on to question number 3. Question number 3, we're finding the gravitational force on between a Kuiper belt object. Okay, basically what we're saying is an asteroid. The Kuiper belt is basically a row of asteroids that exists between the orbits of Mars and Jupiter. So pretend it's like an asteroid. And let's say a small spacecraft like a probe or a satellite or a small spacecraft lands on one of these things. So we're going to find the gravitational force between that little spacecraft and the Kuiper belt object. Okay, go ahead and enter your name in the program so we can begin. Okay, so let's list the information we know in the problem. I'll list mine. So my satellite mass, my spaceship thing is 691 kilograms. And that's going to be mass 1. That's the first mass. My density of this Kuiper belt object is 2391. Density 2391 kilograms per cubic meter. Okay, and the radius of this object is 58.54 kilometers. 58.54 kilometers. Okay, which, if you remember, to go from kilometers to meters, remember your metric staircase, meters, liters, grams, those are all base units in the middle of the staircase. And kilo is way up here. So in order to go from kilo to meters, you have to go down 1, 2, 3 stairs. That means you're going to have to go 1, 2, 3 over to the right. So that would be 58,540 meters would be the radius of this object. Okay, so in the first step, we need to find the volume of this object. Presumably for what? If we find the volume, then we can use density times volume to find the mass. Okay, so we're going to do something similar we did in the last problem. So let's find the volume first. 4/3 pi r cubed, 4/3 pi times radius in meters. Okay, so in my case, 58,540 meters. Go ahead and pause the video, figure out your volume. I'll figure out mine. Okay, well, I have a pretty large volume here. Okay, in my case, about 8.40 times 10 to the 14th cubic meters. Okay, so I got my volume. Now I'm going to find my mass. Okay, so to find the mass, you got to go density times this volume. Density was 2391 in my case. 2391 kilograms per cubic meter. This was in cubic meters, so you can see how they cancel, giving you the unit of kilograms, which is the unit of mass. Okay, go ahead and figure out your mass. All right, I'm getting a value of about 2.01 times 10 to the 18 kilograms. Okay, so what I'm getting for mass. Okay, now once we have that, go ahead and use your gravitational force calculation, G m1 m2 over r squared. And let's get this into the program correctly. Okay, we'll go 6.67 times 10 to the negative 11 times whatever your mass 1 is. Mine is that 691 kilogram spaceship times the mass of the planet or asteroid or whatever it is. And the separation distance between them would be the radius of the planet. Think that through. Okay, if this is your object like asteroid or whatever, and you had some object on the surface of it, the effective separation distance between the center of both would really just be the radius of that object, which we know to be 58,540 in my case. Okay, figure that out in your case. Okay, pause the video right now and go ahead and figure out your gravitational force. All right, I'm getting a value of about 27.03 newtons. Okay, at this point, let's go ahead and put our values into the program and let's see how we did. All right, there we go. Hopefully you were able to get question number 3 correct as well. If you did, let's move on to question number 4. Question number 4 is again another gravitational force problem, but this time it's on a force on a satellite that is some altitude above the surface of your planet. Put your name in the program so we can begin. Okay, let's record all the information available. So for me, I've got a satellite that's 1,203 kilograms. That needs to be mass 1. Okay, go ahead and record your altitude. Mine is 9,114 kilometers, which would be 9,114, 9,114,000 meters. Okay. And then if I go one step further, this is the planet Uranus. Okay. Write that down. Write down your planet. Okay. And then I'm given the mass of the planet, so I'm going to write that down, 8.68. I'll write that down as mass 2, 0.68 times 10 to the 25th power. And then I need the radius of that planet because that's going to help me with the separation distance. 2.56 times 10 to the 7. Okay, now that's already in meters, so you're good there. So question step 2 says, show how you would find the distance from the center of the solar system body to the satellite and explain why you need this. Well, basically it's going to be the radius plus the altitude. So I got to add those together to get my separation distance. So let me figure that out. So my total R, my total separation distance is going to be the sum of those things. So 9,114 Say 9,114,000 plus 2.56 times 10 to the 7. Let's see. I'm looking at 3.47 times 10 to the 367 meters. Okay, so I just added those two together. Okay, and then from that point on, it's just a standard gravitational force problem. So G m1 m2 divided by r squared, open parentheses, 6.67 times 10 to the negative 11 times your mass of satellite. Mine was 1203 times the mass of your planet. Mine was Uranus. 8.68 times 10 to the 25th power. Close your parentheses, hit your divide button, open parentheses, put your separation distance in. That's that basically the radius of your planet plus the altitude above in meters. Don't forget to square it. Okay, and at this point, pause the video and go ahead and figure out the gravitational force at some altitude above your planet. Okay, so for me, I'm getting a value of about 5,784 newtons. And again, when you find the gravitational force on something, what you're effectively finding is how much it weighs. So what I just found is I found the weight of that particular satellite at some distance above the surface of Uranus. I'll put that into my program and see how I did. Go ahead and try with yours. All right, there we go. Hopefully you were able to get this question correct as well. If so, let's go ahead and move on to question number 5. In question number 5, you are figuring out what is called the gravitational field strength. You might remember on Earth, we would call that little g. You would see that present in some of our free fall acceleration problems, right? And on Earth, it was about what, 9.8 meters per second squared, or sometimes you saw it written as 9.8 newtons per kilogram. Well, that's on the surface of the Earth. You're going to find the gravitational field strength on whatever planet you're given. Okay, so let's record the information present first. First, go ahead and put your name in. Okay, so for me, I have an altitude. So we want to find the gravitational field strength at some altitude above the surface, okay, of, now, I don't know what planet this is, Maki, that's different. So 420 kilometers above. So I'm going to write that information down. So 420 kilometers. Don't forget to change that to meters. Would be 420,000 meters. Okay, I need the mass of it. So that would be 4.2 times 10 to the 21st. Okay, and then the radius of this is going to be, let's see, 7.5 times 10 to the 5. Okay, so how do I find the separation distance r? Well, it's going to be the radius right here plus the altitude in meters. So I've got to add those two together. So 420,000 plus 7.5 times 10 to the 5. Go ahead and add those together. Well, I'm going to add mine together. You add yours. All right, so I'm getting a separation distance of about 1.17 times 10 to the sixth power. Okay, how do we figure out gravitational field strength? Well, here's one of the things we learned. The gravitational force is equal to big G times mass divided by the distance, the separation distance between them squared. Well, gravitational field strength is also mass times the gravitational field. Now, since there's two ways to calculate gravitational force, that means I'm going to take these two methods and I'm going to set them equal to each other. That gives me little mg equals big G m1, which I'm going to call the mass of the planet, times little m, which is, I don't know, the mass of anything attracted to that planet, divided by the radius squared. And notice the mass of the object cancels, leaving you with this. And that is how you calculate the gravitational field on a planet. Very similar to the Newton's law of universal gravitation. The only difference is it's one mass. It's the mass of the planet. So we're going to go open parentheses, 6.67 times 10 to the negative 11 times the mass of that object. In my case, not 4.2. It's just 4. 4 times 10 to the 21st power. Close your parentheses, divide. Okay, then open parentheses, put the separation distance. For me, it's 1.17 times 10 to the sixth power. Don't forget to square that. Okay, and when we get there, we're going to get an answer in newtons per kilogram. Keep in mind, this is an equivalent unit to meters per second squared. I'll show you why that's true this week. Go ahead and pause the video at this point and see if you can find your gravitational field strength while I'll find mine. Okay, I'm getting a value of about 0.195 newtons per kilogram. Okay, in the last step, it says explain how the gravitational field strength lets you find the gravitational force on an object placed at that location. Well, that's because gravitational force, and I kind of worked this out already, is mass of the planet times mass of the object divided by r squared. So if I look at that, that would just be the mass of the little object times g, where g is that. I'm going to go ahead and put my information into the program, see how I did. All right, there we go. I was able to get this question correct. I hope you were as well. If so, let's move on to the final question. Force gravity on a planet. Now, we just got done talking about the fact that we can calculate gravitational force two ways. One is using Newton's law of gravitation, which we've been using all along. But if we're on the surface of some planet where we know the gravitational field, then we can just use a much simpler equation, which is just m times g. Now, in many cases, I'm going to be calling force gravity the weight. So many times you'll be seeing me go weight equals m times g. All right, for today, I'm going to go ahead and stick with this. So Don't forget, you're going to be given masses in grams. Okay, so remember, how do you convert grams to kilograms? So from grams to kilograms, we have to go and move the decimal 1, 2, 3 to the left. And then, of course, to go from kilograms to grams, we got to go 1, 2, 3 to the right. Okay. All right, so let's go ahead and enter your name into the program and let's begin. Okay, so for the first question, you're going to be doing a total of 3 questions here, okay? For the first one, it says, what is the mass in grams of a water bottle that experiences a force, that means weight, of 3.420? So I'm going to put that information in my thing. So I have a force. Now keep in mind, this is on Earth, right? So we know the gravitational field on Earth, at least on the surface of Earth. Okay, so 3.420. So my mass, no, not my mass, I'm sorry, my weight, which is the force gravity, which I'm just going to write as F equals 3.420. The gravitational field on Earth is 9.8, okay, newtons per kilogram, okay? And then I'm looking for mass. So just go ahead and solve it. To solve for mass, you got to divide by G. So it's going to be 3.420 newtons divided by 9.8 newtons per kilogram. And if we divide newtons by newtons per kilogram, you can see we're getting kilograms as a result. I'm going to put this in my calculator, put your values in yours. Okay. Now I'm getting a value of about 0.349 kilograms, but you can see we're supposed to be entering our mass in grams. So what are we going to do? We're just going to move that decimal 3 spaces over to the right, and we get 349 grams. Okay, so as you can see, it highlighted my first question as being completed correct. So now I'm on to my second question. Calculate the force gravity, the weight, of a water bottle on the surface of the Earth with a mass of 103 grams. So I'm going to record that. So I have a mass of 103 grams. Well, I got to move the decimal, don't I? So 0.123, that would be 0.103 kilograms. I know that G on the surface of the Earth is 9.8 newtons per kilogram. And I'm looking for the force or the weight, which is just the product of the two. Okay, I'll figure out mine, you figure out yours. Okay, so I'm getting a value of about 1.009 newtons. Okay, you see I got the second question correct. On to the final one. It says calculate the gravitational field of a far-off planet given the mass and the force gravity. So write down your values. I'll write down mine. 398 grams and 2.149 newtons. Okay, so I need to move the mass in grams to kilograms. Remember, we move the decimal 3 places over to the left. So 398 grams would be 0.398 kilograms. Okay, now I am looking for the gravitational field. So I'm looking for G. So F equals mg. So go ahead and divide your mass to get g by itself. And it's the weight, right, or the force gravity over your mass. Mass has got to be in kilograms, though. Okay, and I'm getting a value of about 4.399 newtons per kilogram. Okay. And you can see what I did here. I showed my work for the first one up here. That really belongs down here. The work for the second one really belongs down here. And you can see the work for the third one really belongs down here. So I just sort of did my work a little bit differently. But let's put this into the calculator, into the program and see if I was able to get this right. All right, there we go. Hopefully you were able to get these questions correct as well. Well, I hope you found this video tutorial to be helpful. Okay. If not, please make sure you come and see me and we'll get this straightened out for you. Thank you. See you next time.